Okay, this is another separation of variables example. So I have this dE, dP dt equals p minus p squared. My independent variable is t, my dependent variable is p. So my goal is to get all the p's to the left side, all the t's to the right side. So I need to bring this, I can't subtract. Remember, if you're adding or subtracting, when you're using separation of variables, you're probably going about it the wrong way. It's multiplying and dividing stuff over. I need to get these guys over, multiplying dp. So this is over 1. Just think kind of uncross multiplying. Bring these down to the other side. That's all divided. And then get this dt up to the other side. Now all the p's are on one side, all the t's are on the other. And then integrate both sides. Technically we're integrating both sides with respect to t, but because of chain rule, we can just throw an integral symbol, integrate this side with respect to p, this side with respect to t. So you can check this on your own. In order to do this antiderivative, we have to use partial fraction decomposition. So we have to split this as a over p plus b over 1 minus p. Check those details yourself. You get a and b both equal 1, and we get this. This expression is the same as this. Then we do the antiderivative. Antiderivative of 1 over p is absolute value of p. Antiderivative of 1 over 1 minus p is negative, chain rule, or integration by substitution, negative natural log of the absolute value of 1 minus p. Antiderivative of dt is t plus c. So make sure you believe that one. Here's my implicit solution. If the question asked for implicit, we're done. That's it. I've got an equation that has t's and p's in it. I'm going to go ahead and solve this explicitly. I'm going to solve it for p. Okay, so we can combine these together. Remember, with a log, subtracted outside becomes divided inside. So we have, technically, this is an absolute value. We're going to assume here, just for simplicity, remember we can have multiple solution curves. I'm going to assume for simplicity that we're only taking the right half of our solution. So I'm going to drop the absolute value for now. We could play a similar game with a different solution where we take the left half and all the negative p values. So I'm going to drop my absolute value. So an explicit solution here will be from this. Now we want to convert to exponential form. So I've got log equals stuff. So think of it as make both sides powers of e. E raised to the ln. Those cancel out. We just get what's inside. Over on the other side, e raised to the t plus c. See, it's important to put this constant of integration in when you do the integral. Don't wait until the end and just throw on a plus c at the end, because it won't work. That c needs to be here because that's up now in this exponential. And just like we did in the last video, e to the t plus c could be rewritten as e to the t times e to the c. Well, that's just a new constant of integration. We're going to absorb that together and just call that, give it a new name if it makes you feel comfortable, but I'm just calling it c. Technically, that c and that c are different. It doesn't matter. Okay, now we've got this equals this. Just to get the p by itself, I'm going to cross multiply. Get all my p's to one side. Factor out the p. Divide by this that's multiplying the p. And this is the final solution. This is a really good problem. Try this one on your own. Make sure you can do all those details.